Hey everyone, I am Ms. Hu, your physics teacher. In this video, we're going to be going through the concept of quantum theory of light, where we will learn about how quantum theory was initiated, the quantum theory, wave-particle duality, concepts of photon, and the equations of quantum theory, which include the equations of photon energy and power. Now, before we get started, just to let you know that this is a video lesson designed for students who are taking the Sijil Pelajaran Malaysia or SPM examination in Malaysia. Therefore, this is not a video to discuss quantum theory in great detail. I will only be explaining concepts that are relevant for the students to take their examinations. A little bit of a disclaimer, I am obviously not an expert in quantum theory. And to be honest, this concept was fairly new to me as well when this was first introduced to the new KSSM syllabus in 2021. I have done a lot of reading to prepare my lessons for my students. I have simplified the concepts in a way that makes sense to me and hopefully it makes sense to you. I apologize in advance if there are any errors in this video. Please let me know in the comments below if any corrections need to be made. And now, let's get started. Because quantum theory can be quite confusing, you'll find that my slides are full of memes to help lighten the mood, pun intended. So I'm only going to be discussing the facts. Feel free to laugh at the memes. Here are some famous quotes on quantum physics, and as you can see, nobody really understands quantum physics, even the physicists themselves. So if you're feeling confused after learning this topic, rest assured, you're not the only one. But anyway, let's learn what we can for our examinations. So first of all, let's identify where visible light is on the electromagnetic spectrum. By now, you should of course know about the electromagnetic spectrum, which was covered in the chapter of waves. So the electromagnetic spectrum is quite a large one, consisting of radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, with the visible light spectrum in the middle and taking up only one small percentage of the entire spectrum. That means of the entire spectrum, human beings can only see the tiny spectrum in the middle, and that's known as the visible light spectrum. The visible light spectrum is made up of a rainbow of colors ranging from red, orange, yellow, green, blue, indigo, all the way to violet. There are of course many shades in between, and what you should be aware of is that the entire electromagnetic spectrum, including the visible light spectrum, consists of waves that are made up of waves with different wavelengths and different frequencies. So as we go across the electromagnetic spectrum from the radio waves to the gamma rays, the wavelength decreases while the frequency increases. So for the visible light spectrum, as we move from red light to violet, the wavelength decreases while the frequency increases. Alright, now, so let's get into the concept of a black body. So the definition of a black body is an ideal body or surface that completely absorbs all radiant energy falling upon it with no reflection and radiates at all frequencies with a spectral energy distribution dependent on its absolute temperature. So if you're wondering what this means, let's go into it a little bit more detail. So in the first part of the sentence, it says here that this is a body or surface that absorbs all radiant energy. As you should know by now, we can see color because we see the color that is reflected to our eyes. White light is made up of all colors combined. So in this diagram on the left, you'll see that there's a rainbow of colors here because when all the rainbow of colors combined, we see white light. So we see an object as white because white is able to reflect all light. So when all the light colors enter our eyes, we see the color as white. Black, on the other hand, is the absence of all color. So if white light made up of all the rainbow of colors fall upon a black object, the black object will end up absorbing all the colors and reflecting none of it. That's why we see the object as black. The reason we see color is because the object reflects the color that we see, absorbing the rest of it. So for example, we see an object as red in color because this object is able to reflect the red light and it absorbs all the other colored light. So if we look again at the definition, a black body is an ideal body or surface that completely absorbs all the radiant energy falling upon it with no reflection. That's why we see it as black. But a black body is not just about absorbing all the radiant energy, it is also able to radiate. So let's look at the second part of the sentence and what it means. So let's look at the concept of a black body radiator. Black body radiators can release or radiate heat depending on the temperature it reaches. The sun is a black body radiator. What does this mean? Basically, a black body radiator is an object where if you heat it up until it reaches a certain temperature, this object will start to release or radiate energy, normally in the form of light or heat. So an example here would be like the heating element in your oven. You'll notice that when you switch it on, the heating element will get very hot and it will start to glow at a particular color. So the heating element is an example of a blackbody radiator. The color that the heating element is radiating at depends on the temperature at which this heating element reaches. You'll find the same also for the filament of a light bulb. So when current passes through the filament, it gets very hot, and once it reaches a certain temperature, it will start to glow, meaning it will start to release energy in the form of light and heat. And again, the color that it is emitting depends on the temperature this filament can reach. It is by understanding blackbody radiators that infrared cameras were created. So when we point an infrared camera to an object that is radiating heat, the colors that you see on the infrared image shows us the different temperatures at which that object is at. So for example, you can see that blue color is cold at about 6 degrees Celsius, and at different temperatures, the colors are different. In this infrared image of a car, red color is the warmest at 24 degrees Celsius. This 11.8 degrees Celsius refers to the temperature where the pointer is pointing at the cursor. So what it means here when we say that the sun is a blackbody radiator, the reason why we see the sun the color it is because it depends on the temperature the sun has reached due to the nuclear fusion reactions that are happening on the surface of the sun. Now when we talk about colors though, you have to understand that for blackbody radiators, these bodies are emitting radiation at all wavelengths. You might have seen a similar graph in your textbook. How do we interpret this graph? This is an example of a graph that shows us the different temperatures at which blackbody radiators would radiate at. We have the intensity on the y-axis and the wavelength on the x-axis. On this graph, you'll find various lines, and each line has a temperature written on them. On this particular graph, the temperatures written here are 3000, 4000, 5000, and 6000 Kelvin. What these lines here mean, each graph line is indicating the intensity of every wavelength that the blackbody radiator is radiating. So for example, for the 3000 Kelvin line, it's actually radiating electromagnetic waves at all these wavelengths ranging from 0.5 to 3 micrometers. However, there are different intensities of the different wavelengths, and for the 3000 Kelvin, it peaks between 1.0 and 1.5. For the 6000 Kelvin graph, you'll find that the radiation has a wider range of wavelength, ranging from this value here, very close to 0, not exactly 0, but more than that. And you can see that it goes up, peaks at the top here, slightly about 0.6 micrometers, and then it drops down. But there are still values along here, all the way to 3 micrometers and even more. Meaning, if an object were to reach 6000 Kelvin, it's able to radiate electromagnetic waves at all these different wavelengths. However, the greatest values are about here, as you can see on the peak of this graph. Now, this graph only shows us a range between ultraviolet to infrared. Human beings can only see light in the visible light spectrum. So on this graph, the visible light spectrum is highlighted. So for a black body that reaches about 6000 Kelvin, it actually emits radiation at all the visible light spectrum, which means we can see all these colors. It actually emits ultraviolet, infrared as well. It's just that we can't see them. But for the visible light, we can see all these colors, but it peaks somewhere in the green region, which is why for a black body radiator at 6000 Kelvin, we'll see that it tends to look green in color because that's the color that has the greatest intensity. For a black body radiator at 5000 Kelvin, it also emits radiation at all these different colors, and we will be able to see all this visible light, but the greatest intensity is about red. So that's why we'll tend to see black body radiators at 5000 Kelvin being red in color instead. So that's what a black body radiator graph is showing us. So when we talk about stars, you'll find that they always talk about the color of a star, and you should know that the temperature of a star is proportional to its color. So the reason why we see different stars at different colors is because remember that stars, like our sun, is also a black body radiator, and the colors which we perceive the star to be at depends on the temperature that the star reaches. We tend to see the much hotter stars as blue color, while red color stars tend to be colder. So it is not because red is cold and blue is hot, it is because the greatest intensity of the electromagnetic wave that we see is blue for black body radiators with higher temperatures, while black body radiators with lower temperatures tend to have red as the greatest intensity of all the electromagnetic waves that are emitted. So now that we know about black body, let's go into how the quantum physics theory came about. By the way, yes, this is how I also felt when I was learning about quantum physics. So first of all, let's talk about the classical physics theory. So Isaac Newton was the brains behind the corpuscular theory. He described light as a single stream of particles or corpuscles in 1704. So what is the corpuscular theory? Basically, we view light as particles. Isaac Newton suggested that light is composed of numerous small, fast-moving and elastic particles called corpuscles. His theory also explains why there's a straight line propagation. These corpuscles travel in straight lines, which explains why light travels in a straight line under normal conditions. He also attempted to explain how light was able to undergo reflection and refraction. His suggestion is that for reflection, when corpuscles hit a surface, they are repelled, similar to how a bouncing ball would be, causing the angle of incidence to be equal to the angle of reflection. Whereas for refraction, he suggests that when light enters a denser medium, the corpuscles are attracted by the matter, which causes them to change direction. This also implies that light travels faster in a denser medium, although the point was later disproven. For color, he suggested that the color of light is determined by the size of the corpuscles. For example, red light corpuscles are larger than blue light corpuscles. Newton, of course, attempted to explain how light behaves based on the observations back then, but this was disproven later because his theory was not able to explain a lot of the behavior of light. Thomas Young suggested that light is a wave. Young was the one who conducted a double-slit experiment in 1801 that showed that light is a wave. So if you don't know about the double-slit experiment, please watch my video on the interference of light, specifically the double-slit experiment. Now, also related to how the quantum theory was developed is the atomic model. John Dalton was the one who came up with the atomic model, suggesting that matter consists of basic particles that cannot be divided further, and he called those basic particles atoms. He believed that same elements have the same type of atoms. Later, of course, there was a discovery of subatomic particles, meaning that atoms were not the smallest particles that existed. JJ Thomson discovered negatively charged subatomic particles called electrons in 1897, and he designed experiments to study the behavior of electrons. So in general, what is the classical theory? The classical theory suggests that light is an electromagnetic wave which travels with perpendicular, oscillating electric and magnetic fields that propagate through space. In terms of energy, energy is distributed continuously over the wavefront, and its intensity or brightness of the light is proportional to the square of the wave's amplitude. For wavelength and frequency, the energy of a light wave is related to its wavelength and frequency, which determines its color. In terms of how it travels, light does not need a medium to travel, allowing it to travel through the vacuum of space, and this is a key insight of Maxwell's theory. James Clerk Maxwell is considered to be the person who came up with the classical theory, which explains the behavior of light. Now, many of you will recognize the classical theory because this is what we've always taken light to be, and yes, it's true for a lot of behavior of light. But it doesn't explain everything about light. When they tried to study classical theory in more detail, there was something called the ultraviolet catastrophe. So classical physics failed at the ultraviolet catastrophe because it predicted that hot objects, basically black bodies, would emit an infinite amount of energy at shorter wavelengths or higher frequencies, but this contradicted experimental observations. So this failure was due to the classical assumption that energy could be radiated in any continuous amount, which led to the incorrect prediction that high-frequency radiation would carry an infinite amount of energy. So to resolve the catastrophe, it was Max Planck who came up with the quantum theory. So what is the quantum theory formulated by Max Planck? In terms of the quantization of energy, energy is released or absorbed in discrete packets called quanta and not in a continuous flow. He also suggested the existence of a photon, where the quantum of light is specifically called a photon. In terms of blackbody radiation, Planck's theory successfully explained the distribution of electromagnetic radiation emitted by an idealized blackbody, which was not accounted for by classical physics. Einstein also contributed to the formulation of the quantum theory. In 1905, Einstein proposed that light energy is not continuous, but comes in discrete packets he called light quanta to explain the photoelectric effect where light ejects electrons from a metal. This was a key piece of evidence for the existence of quanta. He was also the first to suggest that light, previously thought of as a wave, also has particle-like properties. This concept of wave-particle duality was later extended to matter itself. He was a co-founder of quantum statistics and discovered the first example of a phase transition using statistical methods. The quantum theory was also contributed to by Niels Bohr. Now, if his name is familiar, it's because Niels Bohr was the one who came up with the Bohr's atomic model, which suggests that electrons orbit the nucleus in electron shells. So his contribution to the quantum theory includes quantized orbits. Electrons can only exist in certain fixed orbits or energy levels around the nucleus, similar to steps on a ladder. These orbits are stable. While in these specific orbits, electrons do not radiate energy and remain stable. There can be energy jumps. An electron can move to a higher energy level by absorbing energy or to a lower energy level by emitting energy. In terms of photon emission, when an electron jumps to a lower orbit, it emits a photon of light with a specific wavelength corresponding to the energy difference between the two levels. These transitions between energy levels are instantaneous and are referred to as quantum jumps. Niels Bohr's model explained the discrete spectral lines of hydrogen. His model, developed in 1913, was the first to successfully incorporate quantum theory into atomic structure, though it was later superseded by the more complex modern quantum mechanics. Yes, there's more to the quantum theory. In terms of wave-particle duality, de Broglie's hypothesis extended the idea of wave-particle duality, which had previously been established for light, to all matter. He suggested that if light can act as a particle, then particles can act as waves. So if you recall, Einstein also postulated the wave-particle duality, so it was Einstein and de Broglie who hypothesized about the wave-particle duality. De Broglie also came up with an equation, and that's how the de Broglie wavelength came about. He proposed that every moving particle has an associated wavelength calculated according to this equation, lambda equals h over p, where h is the de Broglie wavelength, h is Planck's constant at 6.626 times 10 power negative 34 joules a second, and p is the momentum of the particle. Don't worry, we'll be looking at this equation in more detail in upcoming slides. So that's quantum theory and how it came about. Now let's go into quantum of energy. So first of all, let's understand a little bit more about the light spectrum. On this slide, you can see that there are three light spectrums, and actually you do need to recognize the difference between these three spectrums. So the top spectrum here is a continuous spectrum, which is made up of all the visible light colors, and you can see that the gradients in between is because of the changing wavelengths. So this is a continuous spectrum because there is a continuous change of the wavelength from red all the way to violet. So what is the emission spectrum and the absorption spectrum? Different atoms have different emission and absorption spectra. Atoms are not blackbody radiators, meaning that they don't emit light of all wavelengths. Atoms actually only emit or absorb specific frequencies or wavelengths of light. So for example, this emission spectrum of this particular atom would only be emitting light of these particular wavelengths or frequencies. You'll find that the absorption spectrum is a direct opposite of the emission spectrum. That means that when you shine a white light on that particular atom, it will absorb these particular wavelengths or frequencies of light. So for example, if we were to look at the line spectra of different elements, on the top here is the continuous spectrum for us to be able to visualize all the colors of the visible light spectrum. So here are the line spectra of sodium, hydrogen, calcium, and mercury. So all sodium atoms emit these particular wavelengths or frequencies of light only. This applies also to hydrogen, calcium, and mercury. The line spectra is a useful way for us to be able to determine the different elements that exist in a particular object. For example, if you have a particular lamp and you want to find out what element exists in the lamp that's producing that color, if we can obtain the line spectra of that particular lamp and check what colors are being emitted, if the colors happen to match exactly as per the line spectrum for that particular element, that means that element exists in the particular lamp. Now let's go into the concept of quantum. Quantum comes from the Latin word meaning amount. The term quantum means the smallest possible discrete unit of any physical property, for example, energy or matter. Photons are the smallest discrete amount or quantum of electromagnetic radiation. It has electromagnetic energy and it is the basic unit of all light. It does not have mass and it travels at the speed of light in vacuum. So quantum of energy actually refers to the discrete energy packet. So it's not continuous energy. So if you can recall what we've learned about classical theory and quantum theory, classical theory suggests that light has continuous energy. And that's what we always perceive because we see light radiating and we thought, oh, the energy is continuous. But quantum theory suggests that no, light is actually emitting energy in energy packets. So that's what quantum of energy is. The energy that's being released by the light depends on the frequency of the wave. The equation that you would need to know is E equals to hf, where E is the photon energy measured in joules, while h is Planck's constant with the value of 6.63 times 10 to the power of negative 34 joules second. F refers to the frequency of the light wave measured in hertz or per second. So when we look at the relationship between wavelength and momentum of a particle, the Broglie came up with this equation where lambda would be the wavelength of the particle. If you're wondering why is there a wavelength of a particle, remember, we believe in the wave-particle duality of matter. That means that matter can behave both as a wave and a particle, which is why particles can have wavelengths. H is Planck's constant, while P is the momentum of a particle. Now, if you recall what you've learned about momentum, we know that momentum is calculated as mass times velocity, which means that we can substitute this into the equation, giving us lambda equals to h over mv. Now, in terms of light energy, so the equation to calculate light energy is E equals to hf, where E equals to the photon energy, h is Planck's constant, and f is the frequency of light waves. For electromagnetic waves, the relationship between the wave speed c with the wavelength lambda is c equals f lambda, which is taken from v equals to f lambda. Now, c is normally used to represent the speed of light, but as you should have learned by now, all electromagnetic waves travel with the same speed as the speed of light in vacuum. That's why in this case, we use c to represent the wave speed of electromagnetic waves. So if we rewrite this equation, you get f equals c divided by lambda. Substituting this into the equation, that's how we get E equals to hc divided by lambda. So when you know how to calculate the energy of one photon, you can also calculate the power. So we already know that energy of one photon can be calculated as E equals to hf. Now if n is the number of photons emitted per second, the power of the photon can be calculated as P equals to nhf, and then we substitute F equals to c over lambda in the equation, giving us P equals nhc over lambda, where P equals photon power, c equals the speed of light, and lambda is the wavelength of light. So these are the different equations that we can derive for quantum. So now let's just explain a little bit about this wave-particle duality that we mentioned earlier. You'll find that certain matter, for want of a better word, shows the behavior and possesses the properties of both waves and particles. Examples of these include light and electrons. So when we look at the properties of waves and the properties of particles, they actually seem to be contradicting each other because there are certain things that waves do that particles cannot, and certain things that particles do that waves do not. A very simple example I like to give my students is to compare reflection. When waves undergo reflection, there is no loss in speed. The loss of energy translates into a decrease in the amplitude of the wave, but the speed of the wave does not change before and after reflection. On the other hand, particles, which have mass, when they undergo reflection, there's a loss in speed because the loss of energy translates into the loss of kinetic energy, causing them to slow down. So waves do not have mass, while particles have mass. So why we call this wave-particle duality is because we find that light and electrons seem to exhibit both the properties of waves and particles. Now, quantum physicists have not actually found out the real reason why there's this contradicting behavior. So I believe, rather than give a special name for this particular concept, they just call it a wave-particle duality to remind us there could be seemingly contradicting properties that perhaps we don't fully understand yet. Now, proof of wave-particle duality can be seen with diffraction. So on the left here is a picture of a diffraction pattern of electrons through a thin layer of graphite, while on the right is a diffraction pattern of red laser light through an aperture. And if you compare both these diagrams, you'll find they look very, very similar in terms of the diffraction pattern. So this is one of the proof that we have that suggests both electrons and light display wave-particle duality. And that is it for this video lesson. So in terms of how to use the equations to solve problems, I'll put that in another video where I'll focus more on answering questions and solving problems. So if you found this video to be educational and helpful, please click like and leave a comment below on how you found this video to have helped you. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. Do check out my YouTube channel for videos on other topics which you might find helpful. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Subscribe for more free physics lessons from your physics teacher, Ms. Ho. Happy studying!